you ready to go? Okay.
Okay.
Thank you. Thank you.
Okay. So this is the, when they asked for the title, this I had to think carefully about the title. This is kind of the non-provocative version of the title. Let me show you the more provocative version of the title. And maybe this is a little extreme, but so I'm going to talk about a kind of a framework for doing inference, the connection with artificial intelligence, that is the kind of topic of this series of 3 seminars, is that this method actually relies heavily on machine learning. But otherwise, it's not an obvious connection with artificial intelligence. And it's a method that I've been trying to learn for many years, and I still haven't learned it. So I want to tell you today is what the little I have understood. There's a lot of complicated math, but I think it's very beautiful, and I think it's very, very useful. So let me start with an example. So something we may traditionally want to do in biostatistics, or when we're collaborating with, and we want to look at the relationship between an outcome and an exposure, Y and A. And we can think of Y as being binary or continuous for our purposes. And let's stick with a binary exposure A, and we have a bunch of covariates or adjusting variables. And just to fix ideas, and I'm going to be following very closely one of the textbooks on targeted learning. They have an example on Y is mortality within 5 years. So it's a binary outcome, mortality, yes or no, but it's either not, and within 5 years of follow-up. And then the exposure is physical activity, also binarized. It's below or above kind of a minimal recommended level of physical activity. And we have our data, which we conceptualize at least as kind of independent replicates of the same thing. So we sample N subjects, and O stands for, and I'm following notation, the traditional notation for targeted learning. O is the observed data, and we have N units, so N subjects in this case, and for each subject we are observing the trio of the outcome, the exposure, and the vector W of covariance. Okay, so what would we do traditionally if we are faced with this problem, or we have this data and we have to analyze it? So let's assume for now that even it's simpler, so we have a quantitative Y. And we may run a series of linear regression models. So the first one may be an unadjusted model. We have an intercept and a slope and the effect of A, again, which is binary. So that is kind of a saturated model in this case, because we're modeling the mean of the two groups, the mean of physical activity, the mean of the outcome, whatever the outcome is, based on each of the two levels of physical activity. But we typically want to adjust for the covariates, so we can include them in the model. We can do more sophisticated things. Maybe we want to look at interactions, so effect modification. Therefore, we'll include another series of terms in our linear regression model, looking at the interactions. And maybe we want to do something fancier. We want to model the effect of the covariates non-linearly. Maybe we can include splines or some other non-linear function. Now, our interest typically would be in a parameter. So the slope parameter for the coefficient of A, so that'll be the main parameter of interest. And we could fit this model by least squares, which if you assume all the errors are normally distributed and the variance is constant, that would be equivalent to maximum likelihood. And then we'll perform inference traditional way. We will compute based on our software. We can extract standard errors based on the Fisher information, and we can compute confidence intervals, p-values, all in a traditional way. Now, so this is I think it's a fair, maybe a little caricature description of what we traditionally would do. Now, but let's look at a series of problems with this traditional approach. Well, the first is that the interpretation of the parameter alpha A, the slope, is really changing when the model is changing. So in this first in the first model, we're really modeling the difference, the absolute, the unconditional difference between the two levels of the exposure on the outcome. But in the second model, we're kind of modeling it conditionally on the covariance. So the interpretation would be the change in the outcome, the average change in the outcome when we change the A exposure between the two levels, but while holding all the other covariates fixed. So the interpretation is completely different between those models. So our parameter interpretation changes with the model, and we typically fit these models. And so we have a different interpretation for the parameter depending on the model we fit. That already seems a little bit unsatisfactory. And then more issues with that. Who really believes nature is like that and behaves linearly, and we have a linear model, and a linear model really captures things? Well, so we don't believe that. We acknowledge that. That's not a secret. That's not something we hide, but we still do it. We still specify a simple model and we go with it. But what does it mean to have what does the parameter mean when the model is completely misspecified? When none of those models that I put there is a really generated one. So the interpretation is not clear. One can interpret it. There is a theory for misspecified models, and that parameter corresponds to being, so the closest the truth is to the linear model, one can come up with an interpretation, but it's certainly not the one intended originally. And in that case, we'll have a bias in our estimate that's not going to go away with the sample size. And perhaps worse is that the inferences that we're going to make are all going to be wrong. The confidence intervals are going to be too narrow, and also, actually, it doesn't even make sense to compute confidence intervals, p-values, etc., when you have a completely unbiased quantity. The bias could actually easily overcome the standard error size. So in that sense, it doesn't make any sense. And there is a theory of how to do kind of robust standard errors. There are robust methods when you have a misspecified model, so you can a little bit adjust for that. So there's ways around that, but still not ideal. And the other thing that we typically do, I put there that, 4 possible models that we can easily construct. And I think we've all done that. And so certainly in my collaborations, physician wants to look, okay, well, I think there may be an interaction with this, and please try a model with the interaction and without the interaction. And then adjust for sex, and let's see what happens. Oh, sex was not significant, so let's drop that variable. That kind of model selection to a lesser or greater extent, we typically always do. But all the theory of inference depends on having a pre-specified model, not a series of models and choosing one by dropping variables or trying different ones. For the theory to work, you really need to pre-specify a single model and go with it. That's the only work the theory works. And as soon as you start doing model selection, then you start biasing your estimates, and you have the same issues that you had before. The distribution, something that you thought maybe was asymptotically normal, is no longer going to be normal. So all your inference is going to be wrong. An additional issue is that even though we typically want to very strongly say something about causality, the reason we're doing this is because we suspect there is an effect of physical activity on the outcome. But this has been changing over the last few decades. But when I was trained, we should only talk about associations that maybe give you a hint about causation, but the direct consideration about causality was not included. Thankfully, that has changed. There is whole new field called causal inference that allow us to when the effect can be identified, have a causal interpretation. So these traditional models don't really have a causal interpretation. And another issue is that we typically, it's related to all the other ones, the final reporting that we do on interpretation of the parameters is often ignores, not always, often we acknowledge that we fitted 5 models, but less scrupulous practitioners may not report that and may do heavy p-hacking or data dredging and report as if the final model was the only one they consider. And that's really problematic. So I'm going to talk about an approach that I think is sort of circumvents all that, so allow us to move beyond all those problematic issues and in a very elegant way. And the approach is relatively new, but not maybe in statistical terms or how adoption happens is relatively new. It's 10 years old. It is the first book I'll mention in a second. The first paper maybe goes back to 15 years ago. But it still hasn't kind of found kind of wide adoption, I don't think, but I think it should. So it's still a very active research area. So this was developed by Mark McLachlan and collaborators at Berkeley. And they're still at it, sort of developing more complex applications and developing the theory to cover cases where that are tricky. I'm going to talk about kind of the very basic bare bones, so the most simple cases, just to understand what is it that we're talking about. This is my interpretation of it, is that the main feature of targeted learning is honesty, in the sense that we're not going to do all those things that are problematic. We're not going to assume a convenient parametric model just because it's mathematically convenient. We're going to assume essentially a non-parametric model, a model that is infinite dimensional, and that is much more likely to really contain the truth or being closer to the truth that a parametric model that we know is going to be misspecified. And then the connection with artificial intelligence is that I'm going to show you that you can estimate parts, a component of what you need for this machinery using completely data-adapted machine learning. You don't have to do linear regression. You can do your favorite machine learning model. Actually, you can do your favorite machine learning models, and then you can put them all together. And then even after all that data adaptation, all that machine learning, you can still do inference, which to me is kind of magic. Because traditional approaches, so if you do model selection, if you use machine learning methods, typically there is no inference, direct inference associated with those methods. And the method is highly efficient. It's called targeted in the sense that really it targets a parameter of interest I'll talk about in a second, and it results in a very efficient estimator. So there is theory behind that what you're getting is actually efficient. And a nice bonus, even though it's a central portion of it, is you have you can identify your causal effects. You can actually have a causal interpretation of your parameter. You don't have to. You can have just purely statistical interpretation as an association. But if you believe the causal assumptions that I'll talk about in a second are satisfied, then you can have also a causal interpretation. So it kind of resolves all the issues that I mentioned before, at least in my mind. So what is targeted learning? Well, let me tell you first, there are 2 books now on it. The first one came in 2011, so more than 10 years ago, as I mentioned, but the original paper goes before that. And a more recent book kind of extending these ideas to very sort of complex longitudinal studies. I'm still reading maybe a third of the first book. Okay. And if you look, I checked yesterday, I thought there were dozens of papers but there are hundreds of both methodological and applied papers. People are really applying these methods. Okay, so this is stolen from their book. So this is a roadmap just to give you the big picture overview, then we'll get into some details. So we're going to have our data that, in principle, we're going to assume is IID, independent, identically distributed, so very kind of standard data structure. But the method can be used, and they have developed for extended the method to non-true dependent data. Okay, so we have longitudinal data, maybe dependent. I think they did extension to even networks, so they have more complex dependencies. So, but we're going to assume that we're dealing with a classical setting of IID observations. So we're going to have a model. So what is a model? A model is the set of all probability distributions from which your data could have been generated. And typically, we assume a parametric model, as I mentioned before. So we assume that set of possible distributions is indexed by a parameter, low dimensional parameter, or even high dimensional, but finite dimensional parameter, not infinite dimensional. Here we're going to assume it's infinite dimensional. So we're not going to making those constraining assumptions about a parametric model. Then we're going to define a priori a target parameter, something that we really want to estimate that it's not going to depend on the model. It's not going to be like the alpha A. It's going to be something that is meaningful independently of the model. And so we're going to have a target parameter of interest that we're going to define upfront. Then we're going to use machine learning if we want. We don't have to, but it's better to use machine learning because it gives you more flexibility. We to compute an initial estimate of our target parameter. And then this is where the most kind of the new part comes in, I mean, it's all kind of new, the framework, but there's all the heavy theories here. And this is the portion I'll say the least about because it's complicated and I also have a very partial understanding of it, is that you refine your estimator. So you have your initial estimator based on machine learning, and then you're going to refine it. And that refinement gets rid of the bias and makes everything asymptotically normal. And then you can do your inferences and you can proceed as usual, but except that now you have a parameter that is meaningful. So then you do inferences, you compute standards kind of in a similar way that you do for parametric models. And then you'll have an interpretation of your model that if there are causal assumptions that are satisfied, then additionally, in addition to kind of an association interpretation, you can have a causal interpretation. Okay, so that's the basic framework. Okay, so again, in the example before, just let me remind you, so why binary or continuous? I think for this, later on, I want to switch just to binary outcome as an example. And A is binary, and we're going to have the potential confounders. And now we're going to look at, think a little bit in terms of causality. So a parameter of interest in causal inference would be the average treatment effect. So let me say what that is. So the problem with the essential problem of causal inference is that when we have a study, either randomized or observational, is that we would like to see what happens with everybody in the population when we apply the treatment and everybody in the population when we don't apply the treatment, and we compare the two. Of course, we cannot do that, or we cannot. I mean, there are studies where you can do crossover studies, and you do that, but then people change and time pass, so it's not the same thing. You want to hypothetically apply the same treatment at the same time, the same conditions to everybody, and the population not apply it, and then compare. So what we would like to estimate that would be meaningful in this context is the average treatment effect. And this notation means we would like to see the outcome of everybody in the population when we have A, the level of the treatment is set to 1. So this will be physical activity, high levels of physical activity. Contrasted that with the effect on the outcome when physical activity is set to 0. So, but everybody in the population. Of course, we cannot do this because this is a conceptual experiment only. And so, but this is the parameter we would like to estimate in this context. Now, if your exposure is randomly assigned, you have a randomized trial, maybe you can compute this directly. There are some conditions that are satisfied. You can estimate in the way we traditionally would estimate it, which is we'll look at the average of the outcome among those that receive the treatment and compare that to the average of the outcome among those who didn't receive the treatment. This is very different from this for those who haven't been exposed to causal inference, because this is an expectation for the entire population when receive the treatment versus not receiving the treatment. And this is, we're averaging here over the subset of the population that received the treatment versus the subset that didn't receive the treatment, and we contrast that. Now, under some conditions, I'm not going to go over them, we can, the first one is exchangeability, essentially that we have conditional, the importance of this condition is essentially we have no unmeasured confounders. So this first condition implies that W, the set of all covariates, captures all the confounding. And there are other exchangeability, so that's the first one, consistency and positivity. Consistency is kind of more technical. Covariate positivity is that everybody can receive the treatment, yes.
So you could define that ATE as a ratio also, couldn't you?
Yeah, absolutely. So
whatever you're interested in.
the scale could be, this is kind of an additive scale, but it could be on the relative ratio of this. You can compute a causal odds ratio if you're interested in that. So there's nothing about, I'm illustrating that. So the method, the approach with this particular parameter of interest, the average treatment effect, but it could be the risk ratio, or it could be an odds ratio. And in more complex problems, you're going to have to think carefully about what your target parameter is going to be. Okay, so if certain assumptions that allow us to identify the causal effect based on the data that we have, then essentially we can estimate the ATE this way. So I'm not going to go over the derivation, but you can compute the expected value or the average for those that received the treatment or didn't receive the treatment, the counterfactuals. You can estimate using what we traditionally would do. So we have the expectation of Y conditional on the treatment and conditional on the covariates, and outside we average over the values of the covariates. Okay, so if all the causal assumptions are satisfied, then we could identify the causal effect, and we can compute it based on the observed data. Okay, so that is going to be, in this example, the parameter of interest. When I first started looking at this, I was confused because I was thinking that by averaging over W would disappear from this equation, and you're essentially computing the expectation of Y conditional on A unknown. But that's not the case. Here we have the unconditional probability, and here we have a conditional probability. So those two things are different. And a way to think about that, this one is that kind of you're standardizing based on the distribution that you see in your population. Okay, so that would be the parameter of interest in this case. And again, just to summarize what I just mentioned about causal inference, we would like to look at, we observe the treated and the untreated, that this is what we observe. And then these are the quantities that we can compute, but these are the quantities we would like to compute. Those would be everybody's treated and everybody is not treated, and then we contrast those. Okay, so, but if we assume we have a linear relationship, if we assume our parametric model that sort of is the standard practice, and we compute these quantities, you get your data. So, I mean, they are related, but of course, that this being equal to the data depends on the linearity assumptions. In general, they're not going to be the same. So if I compute this for a more general model, it will depend on averaging for different values of W. It will not be that parameter. So that parameter, the parameter of interest in general, will not be correspond to the linear regression. Okay. So, but as I mentioned, we don't believe the linear model, and if we computed the average treatment effect based on a linear model, all our inferences, if we are misspecified, all of the inferences will be invalid. And just to reinforce what I said before, even if we knew that the relationship was linear, in practice we'll try different models and with or without interactions, all the linear regressions I showed in the beginning. And the fact that we're doing all that kind of model searching will invalidate our inferences. Okay. So what's the alternative to all that? What's the alternative that targeted learning proposes? So first, the first idea is to do data adaptive estimations using machine learning of these regression functions. So the relationship between Y and A and W, we're not going to assume a parametric form. We're going to model it kind of non-parametrically. So that's a regression function that we can estimate using our favorite machine learning model. Yes.
Sorry, just to take a step back, because now you're going with the targeted learning. If we assume a parametric form, that's really sort of maybe classical causal inference, like G estimation or along those lines, right? Given a model and the distribution of W, calculate the expectation, the difference. That has been sort of a causal interpretation under a given parametric, where the targeted learning is now saying, well, let's get rid of the specific model and do all of this. Right?
That's exactly right. So yes, other causal if you can identify, but if you believe the true model is linear, then that beta is capturing the causal effect and you're fine. But the problem issue is that we don't believe the linear model, so we're going to dispense with it. And we're not going to assume a linear model. We're going to go with kind of the most flexible thing that we can think of to model that regression. Okay. And so we're free at this point to use any machine learning method that we want. We use additive models, or we can use boosting. We could use even, I don't think it has been used because computationally very hard, so deep learning. You could use anything you want. They can have tuning parameters. You can have, many of these methods have tuning parameters. You can tune those parameters using cross-validation. So something very heavily data adaptive, you can do all that, and there's not going to be any issue. Well, in classical inference, once you do all that, you cannot do inferences anymore, okay? Even better, you can use a long list of, you don't have to commit to any model in particular. You can use them all, put them all in a bag and use them all, and different models with different tuning parameters. You can have models that are stratified. So maybe a variable that you think it's important, you can stratify by that variable. Those will represent different models and you can use them all. And you can choose the best based on use cross-validation to choose your best model. Yes.
Sorry, very quickly. Does it matter? Do you mean independent test cross-validation always, or it could be any form of cross-validation? You know, like, the focus is not necessarily the prediction, right?
No, the focus is not a prediction. Here is on finding a good model for that regression function.
So even if it's the best cross-validation within your data.
It is within your data. You don't have a separate test set, so we're not trying to predict. We're not doing the standard kind of machine learning thing. So, but we still have cross-validation to choose our best model. And I'll go into more details about how to do that. And even better, you can have an ensemble method called a super learner that you run all your models and then you combine them in a kind of the best possible way. And so it's super highly adaptive. And even then you can still do inference at the end of the day, which it's the part I find very magical.
You understand the distinction between doing this and picking the best model as opposed to
choosing or what we were, the earlier version of like, trying to fit different models, different covariates, maybe the covariates must kind of going into that.
Oh, so you could do model selection, the standard model selection, best subset for selection or something like that, and not do cross validation. But the danger, the everything will be okay, except that you're trying to best model that regression that is closest to the truth. If you do best subset selection, etc., you will be biasing. You will estimate. You'll essentially overfit. The issue will be overfitting in that you're not going to estimate this function well. Is the cross-validation component, and that yes. So if you don't do cross-validation, you'll overfit. And you'll be in the same position about choosing a wrong model because you have a high bias. Your model will be very far from the truth. If you do this heavy selection without cross-validation, you'll still be very far from the model because it will be so adaptive that is essentially you overfit. Okay. Okay. So you can use a superlearner. So let me tell you a little about. I know that this is very small. I'll zoom in a second. So this is the scheme of how the superlearner works, and this is nice because this idea of ensemble learning is not new, but it can be applied purely to machine learning. So when your goal is prediction, you can do this, and you'll have probably a better model than any of the individual ones you put in. So how does it work? So let's assume we're going to do threefold cross-validation in this case. And so we're going to split the data into three disjoint subsets. And those are going to be your folds. And each time we're going to be training on two of the folds and kind of predicting in the third fold that we leave out. And so if it's threefold cross-validation, we have our series of models. So here we have four different models. Standard generalized linear models. This is highly adapted lasso, a method that they actually developed based on the lassos, support vector machines, generalized additive models. Let's say that's the library of models that we're going to use. And we're going to train on two folds and predict on the third fold. And we're going to do that 3 times. We're going to have 3 different sets of predictions. And that's what's represented here. And at the end of the day, so we'll have 3 separate set of predictions on 3 different thirds of the original sample. Okay. And then we're going to use we're going to combine those predictions in kind of an optimal way. So we're going to have another regression that I'm not going to go into the details of how it's done. It's actually very straightforward, but is you combine the 3 or the 4 predictions that we have in an optimal way. So we choose these weights so that you have a better estimate than any of the original ones. And in the end, when we have that final model, we fit it on the entire data set, and that's the model we go with. And they prove, they can actually prove that the superlearner actually has kind of an oracle property that essentially, asymptotically, you're guaranteed to find the superlearner is going to be as good as your best model. If you knew beforehand what the best model is, then it will be equivalent to knowing the best model and putting only that one. Of course, we don't know what the best model is, so this is fantastic because we can put them all in and we'll find kind of almost the best model. And this is just to illustrate in their simulation, they have 4 different simulations where they have sort of only one variable x, and we have very nonlinear functions, and they consider this range, this library with all different machine learning models, and the solid lines represent the true regression lines, and the dotted lines represent the superlearner approximations. Yeah.
Is the superlearner as good as the best model, or at least as good? I think it's at least.
Asymptotically is as good as the best model. So when the sample size goes to infinity, it's as good as the best model. So in finite samples, you could be maybe so you still need to do simulations, because in finite samples, you could be slightly worse on the best model, but you're going to be very close to the best model. But the point is that you don't know the best model, so you're going to be very close to it.
Not better.
You could be better. It's guaranteed to be at least as good. Yes, so at least as good.
Is the point, sir, that you will get stable predictions in the prediction world?
It's not about the stability of the predictions. Because yeah, I haven't thought about that. Maybe there is an element of reducing the variability and having more stability by combining most models. But I think the main point in machine learning terms is reducing the bias. So how close you are to the truth.
Yes, and the bias from selecting whatever is the best form of the model, right? This is saying it's going to find out what the shape of that relationship is without you assuming it.
Exactly, without you assuming anything, except that the models that you put in, you're betting on being the truth, being close to one of these models or a combination of them.
And it does matter how you combine them. We're just not going to get into it right now, right? But like
You combine it in a very simple way, but they can show that way has this kind of asymptotic property of choosing being as good as the best. Okay. So here's more simulations they did. These are 13 different kind of benchmark data sets, and they try different individual models and the superlearner, and they look at the relative mean squared error. Okay? So the closer you are to zero, the better, and the best is a superlearner that combines all these models. Okay? The best mean squared error. Okay, so this is an illustration that even in finite samples, you actually perform very well with the superlearner. Okay, so we've done all the work with using machine learning, highly data adapted. Now we're going to have our initial, very biased estimate of the average treatment effect. So how are we going to do that? We're going to have, I'm going to follow the notation. The notation in the book is sometimes hard to follow, but just so that I don't introduce additional notation, I'm going to follow theirs. And we are estimating that regression function using the superlearner. And that estimate that we get, we're going to call Q bar n. And because this will change with the sample size. And how can we estimate the average treatment effect? Well, we can compute we can use that regression function to predict what everybody would have if the exposure was set to 1, and everybody if the exposure was set to 0. We can predict those two, and we can contrast that for every observation, and then we can average across all the observations. And that would be your G computation approach. Typically, if we didn't use machine learning, if you use kind of a model base. So this gives you an initial estimator. Is non-targeted in a way I'll explain in a second. And it's going to be highly biased. And the worst part is that actually we cannot do inference. So typically inference here will maybe use bootstrapping to do inference. Bootstrapping will break down. So this initial estimator is biased, and we have no idea about what the distribution is. So we cannot even do inference if we stop here. So we need to do something better. Let me say a little bit about the targeting versus non-targeting. Is that we're putting a lot of effort in trying to estimate this initial regression function, but our final goal is to estimate a particular parameter that depends on that entire regression function. The way we estimate that entire regression function is minimizing some loss that puts equal effort in estimating every aspect of that high dimensional object or complicated object, without taking into account that in the end, all we want is a single parameter related to that regression. We want the average treatment effect. Okay. So how am I doing time-wise? Very badly. I was afraid I was gonna have, of course, no time, have 40 minutes left. It'll be embarrassing because, but okay. Anyway, So we have an initial estimator, this of our entire distribution. Now we need to move towards our final estimator. So that's going to be the targeted step. And in the targeted step, this is the juiciest part, but it's the part that I understand the least, is where all the math is. And I'll try to give the very vague idea that I understand. So we're going to update our initial regression estimator into sort of a new targeted version that solves an influence curve estimating equation. And essentially, if we have that high dimensional model, so all possible distributions that could generate from which our data could have been generated, and we're going to find essentially one dimensional direction in which we're going to look at our parameter of interest, the average treatment effect, how that parameter changes as the distribution changes. And we look at the direction where that changes the most. And that will be the direction, kind of the worst possible direction, the least favorable model. And we're going to move into that direction. And it's related to sort of the score function. You move in the direction of kind of maximal sort of information. And you do that. I'll show you the mechanics of that, what would in practice that entail. And after you do that, you have a refined estimator of your regression function, and you just plug it in the way you did before. You compute the average among those who receive the treatment. For each observation, you compute the prediction for those who receive the treatment, those who didn't receive the treatment. Sorry, I said it wrong. So for everybody, you predict by setting the A to 1 for everybody, you set A to 0 for everybody, you compute the contrast between those, and you average, where you, instead of using the original regression function derived adaptively, you now updated it. And that update makes all the difference, because that new targeted estimator is asymptotically unbiased, is efficient, and is asymptotically normal. So we can do inference the kind of the standard way. Now, of course, everything I haven't said is because there is a heavy theoretical machinery behind all this that includes sort of functional analysis, influence functions, empirical processes, but I'm still trying to understand. I don't think it's necessary to understand every aspect of it to become a user. So I don't want to give the impression that this is an unusable method, because I'll mention there is software, it's being implemented. But for me, that I want to understand the method maybe to extend it to a particular area of application, it's still complicated to understand all the details. So very quickly, the mechanics of targeted step that's been implemented in software, as I mentioned, but in the case where you have a binary outcome, so the physical activity example, you have a binary outcome that is mortality, you have to, well, the first thing you need to do is compute the propensity. The propensity will be the probability of receiving the treatment conditional on your covariates. And you will do that exactly in the same way you did for the main regression function using the superlearner. And so you have to use machine learning twice here. And then you will define what they call this clever covariate, that is essentially an indicator of having received the treatment divided by the propensity with a negative sign depending on whether you have received the treatment or not. And then the update from your original regression fit essentially fit a very simple logistic regression model that has just one parameter. You get an update. For most models, you need to keep iterating. For this particular version of it, with one update, you already find the optimal, so you don't need to keep iterating. And that's it. Okay. So you have your final estimate. And how do you do inferences? Well, asymptotically, now after the targeted steps, everything is going to be asymptotically normal. So the estimator minus the target parameter will be an average of mean zero functions, and plus something that you can neglect. And so you can compute based on the central limit theorem. We have an asymptotic variance that you can compute. very similarly to the way you would compute the observed feature information. And you have standard errors, and then you can compute confidence intervals, you can compute p-values in the traditional way, okay? So that doesn't change after you do the targeted step. Just to give you an example, in this mortality study, they have, again, I remind you, Y is the death within 5 years of baseline for follow-up, and then they have A is physical activity, and you have a cutoff of the score. They simplify the problem here for illustration to make it binary. And you have a whole set of covariates, and they use a superlearner with all these different algorithms and very different versions of them. So here they have, for example, neural nets, not deep, but neural nets, and they have general additive models, lasso or elastic net with different parameters. So a whole bunch of models. They use that for the superlearner, and they do the targeted step, and they have the estimate, the final estimate is negative. That means under causal assumptions, if the causal identifiability assumptions are met, is that the exceeding or meeting the levels of physical activity will reduce your mortality by 5.5%, okay? So you interpret it in the traditional way, but you also have, in the sense of the statistical interpretation, but you also have the potential of doing the causal interpretation as well. Okay, just to finish up, there is software that implements this. TMLE is the original software back from 2012. I don't know if it's active or not, but there's a newer version where they try to have a general framework based on kind of mimicking the tidyverse, but TL-verse, the targeted learning verse, where you can actually do this, but for much more complicated problems in a form that is kind of automatic, that you don't need to know all the details under the hood and still apply. And just to, I showed you the simplest possible example. They have a full dedicated second book to complex longitudinal data. They apply this to individualized treatment regimes and to mediation analysis. There are all sorts of applications for which they've already developed a theory. And I think many are implemented in the software I mentioned. And so some final thoughts. So first of all, I think I caricatured perhaps the things we do traditionally. And so let me temper that. So the question is, so is everything we've been doing completely wrong? I don't think it is. So if you're careful about what you do, if you don't do p-hacking, if you have maybe 5 models that you look at and you have a decent sample size, your bias is going to be there, but it's going to be small. The problem is when you start doing that in kind of a massive way, when you look at hundreds of different models, that's when the problems really creep in. And some of the parametric method could be actually fairly robust to meet specification, and there's way around computing standard errors when the models are misspecified. So I don't think if you're a careful practitioner, I think what we've done so far is okay, but I think there is better ways to do it. So you could argue, if you were Mark Van der Laan, will be, so why compromise? Why you haven't presented you this method that is better? Well, I think the obstacle, one of the obstacles, the way I perceived it, is that the math behind targeted learning is highly non-trivial. Again, you don't need to understand all the math to apply it. Most practitioners of biostatistics don't know all the math behind the method, so that will be an option. But I think some understanding is helpful, and adoption of something that it's a black box and you don't fully understand is complicated. And for those who want to extend these methods, we really need to understand the theory in a better way, and that's hard, but really interesting. So that's what I've been trying to do. And actually, just a plugin for Daniel, one of the PhD students, he's working on applying targeted learning on a niche area that is actually fairly simple. We can adapt readily the things we already know how to do to G by E, because I think they've been trying to extend this to very complex models. G by E in the simplest case is fairly straightforward, but there's nothing being done on that. So Daniel is working on that, doing a great job on that. So maybe it's a plugin for a future seminar. And with that, I'm going to stop and see if there's any questions. 1 minute over time, sorry. Yeah.
So, trying to understand in this concept, maybe the issue of multiple comparisons and multiple things where you have multiple targeted parameters.
Yes.
So you introduced the idea of A, but then imagine you have A1, A2, A3, and I'm interested in looking at the change of 1, 2 independently, all of them, right? So then this is how you would have to target the parameter. Do I change both? That's going to be at the same time. In the counterfactual, do I change 1? But in any case, does this naturally extend to that? I mean, do you do a multiple comparison at the end of correcting for that? Or is the model naturally handle that because it is modeling jointly that distribution?
So there are two separate issues. One is that in the example I gave, we have a single target parameter of interest. Maybe you have multiple target parameters, and you can estimate them separately. And I don't know, I think you could actually do multiple testing comparison at the end, and the issue will be similar to when you're trying to do inference on multiple related things, but different things.
Yeah.
But a very different issue is what happens when you have a binary, when you have a treatment that has more than 2 levels. And then you have to define a more complicated object because you have to be careful about how you define your target parameter of interest when you have more than 2 levels. It's very clear how to do it that way when you have only 2 levels, but if you have more, it's more complicated. You need to think about how to do that, but you could still get maybe a single target parameter of interest for multiple ones from the same model. But if you have completely separate questions, then you have to do this separately, and you have the multiple testing issue just like we have. It doesn't disappear. Yeah.
2 questions. I guess on that data example that you showed at the very end, that 0.055, is that any different than what you would get in standard logistic regression?
It is. I should have shown that, but they chose that example because they get a different inference. But the point actually is, it's even hard to compare because compared to what? The linear regression with no covariates. But I think they did that comparison, and it shows that the TMLE worked better. But again, the reason I'm saying this is kind of, I think the traditional approach is not bad. Is in our simulations with Daniel, we're finding that unless you do something very extreme, sort of traditional methods sort of still work okay. But this, I think, is very promising, and it's very elegant, and you don't have to pretend things that you don't want. So for me, it's very appealing. But there's a.
You showed your slide with the assumptions again. Exchangeability, early slide.
Those assumptions. So those assumptions will be exchangeability, consistency, and positivity. But those assumptions they are not required. So those assumptions are, so even if you don't have that, your parameter has a well-defined association, not causal interpretation. If in addition you have all those assumptions, then you can extend, but the TMLE machinery doesn't rely on those assumptions at all. Those are identifiability assumptions that come separately.
Yeah, because I was trying to map these onto the example data set that you were showing. Like, I don't necessarily believe that, but yeah. Okay.
Oh, exactly. That example. So you could interpret that causally, or you can interpret that in a pure association if you don't believe the assumptions. Yeah.
I was going to ask, machine learning methods are very data hungry. Is it the same thing for targeted learning? Can you fit this on a sample size of tens, or do you have to have thousands? Like, what have you seen?
I think you need to have decent sample sizes, and I imagine that will be in the hundreds, maybe not thousands, depending on how simple your problem is. So if you have a very complex problem, you'll need more data. But if you have a simple problem like this, maybe, and I don't know the sample size here in this example, but hundreds will probably be okay. Tens, I'm sure it will not be okay.
Yeah, Juan,
Yes.
Can I make comments? Yeah, I want to quick just follow the sample size issue. So when we do the cross validation, okay, a very important issue at the training step is during the cross validation, we are repeating the same model for each for each iteration. And actually, Tishwani group, they did a simulation study. They found when sample size, the training sample size reach about 200, then you can pretty much sure, you do, the cross validation of repeating the similar model, similar enough. But when the sample size drop below that number, there's no guarantee. So if you do threefold, you'll probably validate 3 different models. So that's one comment. The second comment, actually, the question, to you, where the targeted learning, able to automatically detect the unknown effect modifier through a high dimensional data space. So that's a very hard, very, very hard task. Because most of the supervised machine learning, they only targeting to prediction, just predict the outcome. They actually, it could completely ignore the exposure, you are interested.
Well, I think you need to be careful about how you define your parameter. And if you have a high dimensional space of modifiers, things could get complicated. But what Daniel is doing is when you have a space of modifiers that is reasonable, low dimensional, you can definitely use targeted learning. But so the answer to what happens when you have a high dimensional space of modifiers, I don't know. I'm assuming you can make it work, but I'm not sure.
Yeah, well, see, even just talk about 2-dimension, right? 2-dimension, but you have like 10,000 candidate. So that event modifier is hidden within this 10,000 candidate. So are you able to search and efficiently to identify that effect modifier?
Well, I think probably not. So because it will be depend on the efficiency of the machine learning methods, and the machine learning methods have a hard time doing that. The targeted step is not gonna improve on that.
Okay, got it. Thank you.
This works for continuous exposure layers.
Good question, and I think it's actually harder to do. And I think I've seen stuff, but I haven't seen a lot on how to really do the continuous exposure.
Like one estimated dose response curve, for example.
Yeah. So I think what typically people do is just to chop it up in deciles or reasonable quantiles, and then come up with a quantity, maybe say a contrast or something like that. But just deal purely with the continuous effect modification, I haven't seen. Yeah, I have seen a few papers, but it's complicated. Yeah.
Yeah, like the one. So again, the Stanford people, they have the method to search for the high dimensional space. The space about when the exposure to continue is more like a surface. They search through the surface, but that those methods very computation expensive.
Right, but that would be the machine learning part of it. But I think James' question was, how about the definition even of your targeted parameter? What's the definition? Here, when you have a binary exposure, it's clearly contrast. But when you have a continuous exposure, how do you define? So we'll have to integrate or something like that, and it'll get more complicated, or you chop it up. Yeah. Sorry.
So in your final model, you have the linear equation of all the models, and each one has its exposure. Would that tell you which of the models are the better ones? If you could model select that?
I don't know if that's useful. Yeah, the coefficients you could end up with the super learner picking one model and throwing out all the rest. You have that coefficient to be 1, and all the others are going to be 0. And then you learn that model in that particular situation was the best fitting one. But in the targeted step later on, you don't use that information at all.
So I'm wondering about the targeted step that involves estimation of the propensity score. I wonder how the superlearner works. I imagine it tunes or chooses the models based on the usual predictive performance measures.
Yeah. So that's a good point. I know you're interested in looking at the propensity and using measures of performance. that are about balancing, having a propensity that balances things, and so you use very different measures. They use traditional approaches. They use AUCs and things like that to compute the propensity. So there is a potential of improving the computation of the propensity score that will go into the influence function and the targeted step. Yeah.
So, like for conventional regression analysis, if you do your analysis in 2 different samples, and then you get your effect estimate, and you compare them across the samples, and you notice they're different, if the difference isn't due to random error, then I think like I would assume it's different due to the covariate level distribution is different between the 2 samples. And there, since your model is the same between the 2, you can kind of, that's where the change might be coming from. But here you have that the model is changing between the 2 analyses too, potentially.
Because you have the 2 levels of the covariate, because you're not splitting the data for your final and targeted step. So I'm not, yeah.
So the models, the same models used for both of the counterfactors.
Oh, no, I mean, like, somebody does a study in New York, and then somebody does a study in Los Angeles, and then they're like, our effect estimate's different. And somebody could say, well, smoking prevalence is a little bit different in New York, so maybe that's why. But both you guys use logistic regression models, your exposure linear. So we know it's not from them. So here, is that not an issue at all? Where now you not only have the covariate distributions potentially changing between the studies, you also have how the modeling technique uses them to build the estimation.
I think that's a great question. What I think is the opposite. It's kind of when you're using a logistic model, and in New York they use a logistic model with one covariate, and here they use a logistic model with another covariate. Then you're comparing the 2, but they change unless you use exactly the same model.
Yeah.
Here, you're looking at the average treatment effect, and all you do before is just a means to estimate that. You're estimating the same quantity.
Yeah. Yeah, but I mean, that ideal never really exists where you have one actual population parameter, right? And then that population is perfectly randomly broken up into a bunch of smaller samples, right?
You're talking more about replication, aren't you? Replicating looking like.
Oh,
So let me, I think you have so still this assumes IID models that things come from a particular distribution, that you're doing your sampling, you have an observational study, you haven't done any sampling. So that's common to all statistical issues, all statistical methods. So this doesn't correct for that. So you still have to examine why the estimates are different in 2 different places. The distribution of the covariates play a role here because you're averaging over 2 different distributions. You're averaging over when you compute your estimate, your raw and your targeted, you're averaging over the distribution of the covariates in your sample. But you have 2 different distributions of covariates. I don't know if it's done, but you could actually standardize them to a common distribution if you wanted.
Okay.
You could easily do that.
Yeah, that was a good idea for Philip. So
Yeah. Yeah.
Positive of this algorithm so that I make sure I understand it. So we get a data set and then we partition it into 3 sets, for example, and then we fit dozens of models and then use cross-validation to do prediction on all the data points. So for each data points, we will have say dozens of prediction, each from one candidate model we want to fit. And then next step for each prediction, we will have kind of a new prediction, which is a linear combination of the prediction from all the candidate models.
Yes.
And then we will check the, say the mean square prediction error or other.
We won't. So I'm just showing you. So in those simulations, I'm showing you that they computed that just to illustrate that the superlinear is actually doing its job. But in practice, you don't necessarily have to look at the mean square to see if you have this. You're trusting the superlinear will do its job. maybe you look at it for diagnosing purposes, but not because it's part of the intrinsic part of the algorithm.
But for the linear computational, that's where I'm.
Because I didn't say that they use maximum likelihood. They have a simple logistic model with no intercept just to combine them, because those are predictions. You have probabilities, predicted probabilities, and you have you can find an optimal convex combination that minimizes. Yeah.
The data and the predicted.
Yes.
Value, find the value of the best.
Absolutely.
Of coefficient.
Yes.
So that fits with this part.
Yes.
Okay, so that's what it fits.
Yes.
And then, my last question, I was missed when you talked about the uncertainty of your inference. So I remember you mentioned about uncertainty. But in my opinion, like you fix the coefficient for your linear predictor, so the uncertainty actually comes from each component, like each predicted model, right? So how you do
So I think the beauty, which I still don't have a perfect sort of good intuition, is that you can do all that model selection, choosing those optimal parameters, and then you have your initial estimator and you reset, and your initial estimator, you treat it as your data. You then kind of fluctuate your model but moving in the direction of the influence function, the score, and then now you have an estimate that is going to be unbiased and asymptotically normal, regardless of everything you've done before. So it looks incredible, but it's true. Because I mean, I tried the simulations too. I've seen Daniel do the simulations, and you look at a QQ plot, you look at the original estimator, the untargeted estimator, and it's not going to have a normal distribution after all that work you do, all the selection, heavily data adaptive selection you do. That estimator is going to be biased, and it's not going to be normally distributed. You do your targeted step, and magically everything is asymptotically normal, and you don't have to care about whether you fix the parameter. You do the super learner because that's your best shot. But you could decide, okay, I'm going to go with just logistic regression, just with that. And if you believe that, if you have reason to believe that's the best model, you can do everything you've done it without doing the super learner. Yeah.
So, okay, yeah, that's, I'm curious now, how the super learner works. It seems like if you don't benefit too much from having a model that's a subset of another model necessarily, because
You
the
don't.
linear model can pick it up, then the generalized linear model can pick it up, right?
Right.
So, could you just replace all of that with a massive neural network? Like, if you had a massive neural network as one of your learners, would you need any others?
I assume you don't. I assume if you have a deep neural net that is better than all the others, that you go with that. Now, you have to do cross-validation here, and if you want to analyze the data as you have a large data set, there's computational issues. And then you have to do it multiple times, and you need to fit not only the regression function, but the propensity score is also, that would be another neural net. So it gets into computational issues, but conceptually, yes, you don't need to put all those models. But also, it doesn't hurt, so you could throw them all in.
Right.
Yeah.
Really
Yes.
unlimited.
So there's a lot of interest in this. We're going to have him talk next week. Maybe we do have a third week, since we have like an opening where Jen comes back, and we could have maybe just a discussion, not just like thinking about this, and whether people are interested in, have the time to come back on the third day.
Very interested, but I'm not going to be around that week.